So what we are going to do today is talk about some sigma notation. Why in the world would we need to talk about sigma notation? We're eventually going to build up to this concept of area under the curve. Okay? And so today we're going to talk about sigma notation and how to do some shortcuts with adding sums. We're then going to talk about using different shapes to approximate area under the curve. And then we're going to kind of squish the two concepts together to get the exact area under the curve. And then we'll come back to integration and how it relates to all of this. Okay? So we're going to kind of build. It's going to seem strange to you until we put it all together, and then you'll be like, oh, that's why we did that. Okay? So pretty much enjoy today, because we really don't do any calculus. All right. So you have seen series both in Algebra 2 and pre-calculus, but let's just go over what all the notation means. All right, in a sum. So this is the letter sigma, the Greek letter sigma. It means sum in mathematics. Okay. You're going to have something down here. It's going to be your lower limit. K equals 1, K equals 5, K equals 17. That's what you're going to start plugging in. Whatever value is up here, that is your upper limit. That's where you're going to stop. And then you have a function inside indicating what you're plugging into. Okay, whatever letter this is right there is indicating what you are plugging into. So since this is K, anywhere there's a K, you're plugging in that lower limit, and then the next integer, and then the next integer, and then the next integer until you stop at this number, and you add all of those together. Okay? For example. Okay? And I wouldn't write this down up here. Okay? This is kind of what we've been talking about. But I equals A. I is the variable that we're plugging into. We're beginning at A, we're stopping at B. And so we plug in each of those numbers until we get to B, and we add them all together. So write this down right here. The sum from K equals 1 to 5 of K squared. And I'll say that again so you can hear how I say it. The sum from K equals 1 to 5 of K squared. So what does that look like? Okay. 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, which is, yes, 1 plus 4 plus 9 plus 16 plus 25, which equals 55. Okay. How about this one? The sum from K equals 3 to 8 of 7. It's your 7? just equals 7. When k is 3, what's our function value? When k is 4, what's our function value? When k is 5, what's our function value? So we have 7 plus 7 plus 7 plus 7 plus 7, 6 times. We have 7 for k is 3. We have 7 for k is 4, k is 5, k is 6, k is 7, k is 8. 8 sevens. Okay, so just so we can get back in the groove with all of this notation, we're going to do some practice. Write it down. The sum from k equals 1 to 8 of 2k. What did I say? It's k equals 3 to 8. Sorry if I confused you. Okay. Here, we have 2 times 3 plus 2 times 4 plus 2 times 5 plus 2 times 6 plus 2 times 7 plus 2 times 8. What is it? 56? Oh, you got math. All right, here's one with a different letter just so you can get used to the idea of it doesn't have to be K, it could be anything. The sum from I equals 2 to 4 of the quantity 2i squared minus 3. Okay. So we have 2i squared minus 3 plus 2i squared minus 3 plus 2i squared minus 3. And once we get to 4, since that's our upper limit, when we stop, what's I sum? 49. One more, and we'll talk about some properties of sums. All right, the sum from k equals 1 to 3 of k sine of k pi over 2. So we would have 1 times sine of 1 pi over 2 plus 2 sine of 2 pi over 2 plus 3 sine of 3 pi over 2. Luckily, you all know your unit circle very well, right? What's the sine of pi over 2? 1. What's the sine of pi? And what's the sine of 3 pi over 2? Negative 1. So this sum is negative 2. It's okay to have a negative value for a sum. Yeah, negative 1. Okay, now, if I'm going to talk about a summation in general, okay, I might use some subscripts, okay? So when we talk about a summation instead of a function, we typically call that a sequence, okay? We're taking the sum of a sequence. And if you remember back to pre-calculus, sequences we named by usually a sub n, sometimes b sub n. So in general, if we're talking about a sum, we'll use kind of that sequence notation, okay, where we have b sub k is just notating any term, and then when we specifically plug in values, we have the first term plus the second term plus the third term all the way to the nth term. Okay. Now, I'm going to talk about some properties. These three properties you've seen in pre-calculus, even without seeing them in pre-calculus, or if you don't remember, I feel like they're somewhat intuitive. Like, okay, I would have assumed that anyway. But just so we formally talk about it, okay, we have three properties of summations. Here's the first one. If we have a constant inside of our summation, we can bring it to the outside, do our summation, and then multiply by that constant. Sound like something we've used recently? Okay. Okay. The next two go hand in hand. First one, if there is addition inside of our summation, we can break it apart into the sum of two summations. And then since addition and subtraction are viewed as equals, I'll just go ahead and show you the next one is the same thing with subtraction. So you could even squish B and C together and just put plus or minus instead of having to write both of them. So I'm going to go through two examples of how these can be used, okay? And then we're going to get to the good stuff. I'm going to show you some shortcuts for summations, okay? So far, I've given you, like, what, at most 5 or 6 terms you've had to add together. What if I give you a summation from 1 to 100? Want to add those all together? No, not really. I don't think you do, okay? So let's just do 2 simple examples, and then we'll get to some shortcuts, which is what you want to see, right? So using the properties that we just talked about, if we have the sum from k is 1 to 3 of 2k, what we can do, and some of you may not view this as a shortcut, and that is fine, is we can bring that 2 out in front, and we can multiply 2 to the sum of 1 plus 2 plus 3. Okay. Doesn't seem like a big deal right now, but if that were a sum from 1 to 100, it would be a big deal because I'm going to show you some shortcuts you can use. Same thing here, if we're doing the sum from 1 to 4 of k minus k squared. It is okay to break this apart into the sum of k and subtract the sum of k squared. Might not seem like a big deal right now, but when we get to our shortcuts and we have a very large sum, it could be helpful. But it's going to be nice here too. So we can break this into 1 plus 2 plus 3 plus 4 minus 1 plus 4 plus 9 plus 16. Okay. Well, it makes it kind of nice because we can see pretty easily that 1 minus 1 and 4 minus 4 cancel out. And now we're left with 5 minus 25. Negative 20. All right, some of you are getting bored. I don't blame you. Ready for the shortcuts? These shortcuts are important. And I'll tell you right now, they will be quizzed on over on Wednesday. Gotta get our new schedule under control here too. Okay? First one. If we have the sum of k, which is like 1 plus 2 plus 3, you know, all the way up. We can rewrite it as n times n plus 1 over 2. The sum from k equals 1 to n of k can be written as n times n plus 1 over 2. Some of you recognize that a little bit from when we did arithmetic sequences in series. If you don't, not a big deal. When we did arithmetic sequences, when we did arithmetic sums, first term plus last term times the number of pairs that you have. Okay, yeah, so we proved some of these things using mathematical induction. You're exactly right. If you're summing up k squared, you are summing up k squared, your shortcut is n times n plus 1 times 2n plus 1 all over 6. Okay, some of you might be thinking, oh my gosh, how am I going to remember all of these? As long as you can keep these two squared away, then for the k cubed shortcut, it's just the k shortcut squared. Okay, so there's really only two different fractions to memorize because you just take one of them and square it to be, well, specifically the k sub, and square it to be the k cubed sub. Like I said, you do need to remember these. You will be quizzed over these shortcuts on Wednesday. Okay, we're going to do 3 basic examples. on the next page. Probably one for each of the ones that we're talking about here. Okay. If you have a sum that's 5 or 6 numbers, you know, it's really not that much more work to do the actual sum than the shortcut. But if we're talking about, you know, double digit, triple digit, quadruple digit numbers for sums, for sure you're going to want a shortcut. Okay? So first one, the sum from k equals 1 to 23 of k. Okay? So our k shortcut is n times n plus 1 over 2. What is n? 23. That's where we stop. So what's n plus 1? 24 over 2. Essentially, we have 23 times 12. 24 divided by 2 is 12. What's 23 times 12?
176.
Alright. Next sum. The sum from k equals 1 to 7 of k squared. This sum might not be too bad, but we'll just use the shortcut so you can see how it works. Alright, the shortcut for k squared is n, which is times n plus 1. 8 times 2n plus 1. Over 6. So you have 7 times 4 times 5.
140.
What is it?
140.
Right, because 6 is 3 times 2. Do you agree? So 2 cancels here to be 4, 3 cancels here to be 5, so you have 7 times 4 times 5. 140. Okay. Yeah, you need your calculator, but you don't have to. All right, the last sum. Let's practice a k cubed. This summation, k equals 1 to 6 of k cubed. All right, so the k cubed shortcut is just like the k shortcut but squared. So we have n, which is
6.
n plus 1
7.
over 2, and then you're going to take that and square it. So it looks like we have 21 squared, which is
41. Just 141.
all right.
Is there a reason that works?
I don't know.
It's kind of crazy.
Jackson just had a moment. 21 squared is 441. 12 squared is 144. Isn't math beautiful?
Cool.
I don't know the answer to if there's a reason for that or not. But it's definitely something to look into.
Yeah.
Have me thinking now. That's just pretty beautiful. All right. What if we have something like this? Please do not sit there and plug in 30 numbers and add them together. What could we do based on the information that just went through? Think about your quiz. All right, we can distribute to where we have k squared plus k, right? So we can use two shortcuts. We can do the sum from k equals 1 to 30 of k, and then we get squared, and we can add it to the sum from k equals 1 to 30 of k. So we distribute it and multiply it through, and then we can break it apart into individual sums so we can use our shortcuts. Okay. So our k squared shortcut is n times n plus 1 times 2n plus 1
61.
all over 6 plus our k shortcut is n times n plus 1 over 2. Here's one we might want to see. You'll have a calculator on your quiz, so it's not a problem to practice with it. Anyone have a number for me?
9,920.
There we go. Okay. Now, I know some of you are thinking, Mrs. Holman, I have a button on my calculator where I can type in a summation. And I know that. You do. I don't really care if you know how to use it, but to build up to where we're going after our quiz, I would like you to know these shortcuts so that we can bring them together with our integration. Okay, eventually this is going to lead up to definite integration, right? Yesterday's quiz was about indefinite integration. We're building up a week-long build up to definite integration. All right, now 2 more slides. Hang with me here. If I'm talking about the shortcut of a summation, okay, so this is the sum of k squared from 1 to n, right? Here is the open form. Okay, would this be called open form? It's long. Okay, we don't know if it's in terms of n. We don't know how many numbers there really are. It's pretty open, right? Closed form would be the shortcuts that we just talked about. Okay, it's a definite. Even though we don't know how many numbers we're summing together, we have one term to actually express it. Okay, instead of who knows how many. Right? So I just want to practice writing a summation in this closed form, even if we don't know how many numbers we're adding together. Okay? So what I want you to do, make sure all our pencils are done, go ahead and write down this summation. K equals, the summation from k equals 1 to n of 3 plus k to the quantity squared. Do we have a shortcut for 3 plus k to the quantity squared? If we multiply it out, what does 3 plus k to the quantity squared multiply out to?
9 plus k squared. Oh, 6k.
Yeah, you just weren't done. It's fine. Yeah, you're getting there. Okay, 9 plus 6k plus k squared. Okay, so now we have the 3 different shortcuts to use. Now this would be my suggestion, okay? And this is what we talked about before. Break it up So the sum from k equals 1 to n of 9, plus, instead of writing the sum of 6k, let's go ahead and write 6 times the sum of k. Because we know the shortcut for the sum of k, then we can multiply it by 6. That is why we wanted to talk about that property. Now, one shortcut we haven't talked about. The sum from 1 to n of 9. How many times are we adding 9 together? N times. What did you say?
I said it's the n times. Like n times.
I'm with you. All I heard was n, so I was like, I
Yeah.
don't know why that was funny. Okay, n. The n times. Okay. Second, the sum of k we know to be n times n plus 1 over 2, but then we have to multiply it by 6 because we have that 6 out in front. And then our k squared shortcut we know is n times n plus 1 times 2n plus 1 all over 6. So now no matter what our end is, we can plug that number in and figure out that sum. Not a problem. All right, what do you think? Nice little break? Oh, nice little break from calculus. Okay. So you have Paula? Yes. Sure thing. Here, can you go see Mr. Johnson? I would take your stuff because Bill's gonna ring here soon. Okay, so you have a book assignment. I don't think it's very long either. Tomorrow we'll talk about area under the curve and approximating it with the rectangles. So please come in tomorrow remembering how to find the area of a rectangle. Can you do that? Okay.